All right, so thanks everyone for joining our ridiculously named talk. For those of you who are wondering why our first slide looks like that, that is what happens when somebody tells me that my first slide is too boring and I needed to make it more interesting.
I think it looks perfect like it is.
Yeah, so if any of you know Soldier of Fortran, it was him who told me it was too boring. And to be honest, oh wait, is this working? Does this work? Do I get a clicker?
That is
I
the
get
clicker
a
I gave you.
clicker.
Okay.
I'm happy. This was the original slide, so I get it. But epilepsy aside, thank you for coming to see our talk. Larry, if you want to.
Okay. So normally we go past the introduction thing, but yeah, thank you guys for coming and watching us demonstrate how we can actually make laser fault injection and some other laser fault tools available for the masses.
It was the thesis joke that you
Oh.
normally do. It's been
Sorry,
a long day.
it's been a
for
long
us.
day. So this talk is being categorized by a few people as 5 theses in a trench coat trying to sneak up on someone. So there's a lot to cover here, and we don't have long. So I normally make a Smoking the Bandit joke about having a long way to go and a short time to get there. So unfortunately, I fumbled that. So
It's okay. When we created this research, we had to consolidate about 9 PhDs to altogether within 2 months of time because we thought we would have more time. But we'll cover that in a second. For those of you who are more familiar with our talk, we did deliver this last year initially at Black Hat. The only reason why I mentioned this is we have made some modifications to the slides. So if you have any questions or you feel like we haven't answered any questions during this talk, feel free to have a look at the video slides there for no other reason than I promise you that's not malware and that wasn't just like a totally great way of phishing you. All right, so.
and it's got little cute dinosaurs.
We get asked a lot of questions about how on earth we got around to actually naming the title the way we did. So what you're seeing right now is every single title we came up with when we were given an hour worth of notice to name the talk because
We submitted, we filled out the fire forms, we had everything working, and then we forgot the title.
yeah.
So it was not exactly last minute, but it was like within the last 5. And so we were just frantically typing things while at 3 o'clock in the morning after going to the bar, which is why a number of them are just named Pew.
We really, really wanted to get the lasers go pew pew thing. So we're really, really happy that we got it in. But that's kind of how it happened. It was late nights, totally sober decisions, and absolutely not last minute working out. So
And not high on gummy bears, no.
before we get started, let us introduce to you who this team is. So we call ourselves Project Lorem. As you can see by some of the photos, Larry and I have actually worked together for a very long time across multiple companies. And we always used to make the joke that if we ever did a major research project together, we would call it Lorem. And that's because he hates me.
So whenever Sam's working on a report or a document or a spreadsheet or anything else not finished, obviously put Lorem in there. So now Lorem is on every single document associated with this in every single place it possibly can, and she can't fix it.
Yep, and the worst thing about having Lorem as the project name and the placeholder is I use that to define something not finished, and a year later, this still isn't finished. So I really am having the time of my life with this. But of course, once we named it Lorem, we had to figure out what to call it. So we totally didn't absolutely use ChatGPT for this, but it came up with laser oscillation for retrieving electronic memory, which we actually think was pretty accurate to what the actual tool was meant to be.
It works.
It works, yeah. Okay, so a bit about me. My name is Sam Beaumont. I go by Panther, and I'm kind of known as the woman who never sleeps. I'm always tired. In fact, most of you saw me tanking a Red Bull over there. I definitely wasn't out in Vegas at 5 a.m. in the morning and waking
There's
up at
a spare
7 a.m. in the
case.
morning. He does have spares. And the way that Larry kept telling me to come to B-Sides was, hey, they have an entire fridge full of Red Bull for you in the speaker area. I am terrible with nouns, so for any of you who ever want to say hello to me or maybe have known me or worked with me before, I will tell you I'm terrible with anything with a noun. Even if you are my best friend, a common household object, or like something else, I will forget it. So please continually speak about yourself in third person. Otherwise, I'm going to consistently try and go through your entire life story trying to figure out what your name is when we are having a conversation. So please, talk about yourself in third person.
So I'm Larry Trowell. I have a horrific memory for acronyms. I can't remember what any of them stand for, partially because of dyslexia. I also am a specialist in all embedded systems, whether it's medical, financial, video game. I'll hack anything with a chip. And the thing we put about here about me is that I have the most unique sense of direction. Doesn't matter how I try to go somewhere, it'll be the randomest way. I'll follow someone random and I'll end up exactly where I'm supposed to be, even if I'm completely lost.
We call it the hand of God navigation, because honestly, it doesn't matter where you're going. Larry will make it there eventually and in time. Just, one story is I asked him where he was, and he told me he was following a little family of people through the streets of London and somehow made it to the bus station that was 3 blocks away. Because reasons. Okay. Project Lorem is made up of 3 additional people who are not here today. The first person who we really wanted to shout out is a man called Chaz Becht. The S is underlined because Chaz is not a real word or a real name as far as all autocorrect systems go. And so every single time I talk about Chaz, it always autocorrects to chassis, every other type of Chaz except for Chaz.
I didn't know chassis. That's what I'm calling it from now on.
Chassis. We call him Chaz GPT, so if you hear us say that joke, it's literally if we don't know something, we ask him, because he really helped us with the electrical engineering part of this, especially when we had some problems with the laser at the very beginning.
Yeah.
The second person is Casey Rep. So Casey really allowed us to bring this open source and online to the community because, as I'm sure all of you know, documentation is real hard. And it's really easy to do the thing compared to actually writing about the thing. So he's our Android and also known as the second Sam, because every single time people meet me and Casey together, they think I'm Casey and he's Sam, and we end up just going with it.
And occasionally gets sidetracked and he starts telling stories with puppets. It's the weirdest thing. Don't know where he keeps them.
And the last person we want to introduce is a man called Curtis Shelton. I emphasize the T-O-N at that because for 2 years, until about 24 hours before the Black Hat talk last year, I thought his name was Sheldon. So I had been calling him Curtis Sheldon the entire time. And he never corrected me for 2 years because he thought it was just all part of the joke.
It's on you.
So Curtis was instrumental to the research because he allowed us to come up on stage and talk about artificial intelligence and or machine learning and not look like complete morons. So a little bit about that later on in the talk. Together, we are a team of 5 people who specialize in hardware and integrated systems, also known as hardware and embedded systems, and artificial intelligence and machine learning. And at the time of the project, we all worked for the same company. So NetSpy, we're a security services company. I'm not gonna spend much time on this, but we do a lot of specialist pen testing services from mainframes to AIs to hardware. So if you're interested in talking to us, let me know after the talk. All right, and a very special thanks just before we end. We wouldn't be here without these 2 individuals, John McMaster and Dr. Matt Lindley. John was our emergency acid supplier, cough, not the fun kind, and cough, where we ran out of decapsulating material. And Dr. Matt Lindley was available for us at 3 a.m. in the morning when we broke something. That wasn't expensive.
Yeah, no, totally wasn't. Wasn't very pricey. Nope.
Okay, so you guys all came here because you wanted us to talk about lasers.
So, before we get started with the lasers, we're going to have a little bit of a legal disclaimer.
You've got about 30 seconds to read this OSHA document that tells you everything you need to know so you don't come sue me because I don't have any money and that's why I wanted to do this
Don't
thing.
worry, everything here is legally binding.
So for those of you who don't want to read.
Very sorry, but you did ask for a cup of sanity. Unfortunately, in the most ironic thing ever, I ordered a mug that said, cup of sanity.
Yeah.
And it was unavailable and it didn't come. So you got this.
Sanity is back ordered. Okay.
Thank you. Cheers. I really hope this is straight up vodka.
It is. I could get that if you want, but that's just water. So I wasn't sure.
Thank you very much.
So usually by this time, we've gone past this slide, so you couldn't have read all of it. But if you happen to notice the rim everywhere in there, good job.
I really needed to fill that slide out. All right, so really, there are 4 things that you need to take away from this and not sue us from. The important thing about working with lasers is, number 1, you can be blinded or worse.
So even though the light is invisible to the naked eye, it will still burn you and blind you.
You must wear protection.
And you probably, if you're lucky, only have 2 chances to protect your eyes.
And because we cannot just demonstrate to you why lasers are so dangerous with your optical eye, we chose to instead use a digital sensor instead.
So if you look at the images here on the left, you see people filming various concerts where they have laser displays. And all those little black lines you see are pixels that will never be populated because the sensor has been burned out of the actual phone.
And our eyes are more sensitive than digital sensors. So please, lasers are dangerous because if you do not follow the practices that we
Laid out on, and you look at it with black on the left, you'll end up like Beaumont on the right.
Yeah. Okay, so, not talking to me. Hands up, who knew that laser was an acronym? Nobody likes a show-off, guys. So talking about all the different types of lasers and what they do is out of the scope of this talk, but we wanted to briefly comment what a laser is. So laser, as all of you show us knew, is an acronym for light amplification by simulated emission of radiation that I totally had to read off my own slide.
So basically what that means is if you pump enough energy into a lasing medium, out will come a laser beam, which is a coherent beam of light that you can use to focus and target things, in our case.
I just remembered you're not Carl. Sorry, I figured it
Okay,
out. I'm bad with names. I figured it out. That's so sorry. All right. So why lasers and why would you use that? Why would you use lasers against hardware material or in hacking or pretty much in anything that you use lasers for? Yes. Yes.
True. That works, yes.
That is the super clever answer. Our answer is it's easier to source.
And it's also easier to target if you're doing with heat. It's a lot easier to get a targeted light beam than this actual heat-sensitive beam. And basically, we're going to go into the fact that how transistors are all just very poor photodiodes. As you said, you put enough energy into it, it charges up, and it changes state.
Transistors being what holds memory within chips. We'll get into that later. Lasers are typically completely contactless, and they are typically non-damaging physically to the target if used correctly.
And typically you use these in a manner that's called a semi-invasive technique.
So what do we mean by the word semi-invasive when using lasers in the context of hacking? Well, when you're prepping a target to receive a laser, there are traditionally 2 different ways that people like to employ. The first way, which is my favorite way, is using chemical decapsulation, where effectively you take a not the fun kind of acid and you use it to eat away the top layers of an epoxy that holds the silicon dye, exposing it to the outside elements, i.e. a laser, so it can receive it from top down. Or method number 2, being Larry's favorite.
Brute force. We're talking sandblasting, we're talking extreme heat, or in the case of our favorite method, zip socket on a power sander. And if you watch, we love this one because you can see this is a failed attempt that was completely safe. Those are safety hands. And the safety goggles are on there, Julian's head. But you see little wires popping out? That's when he's gone a little bit too far.
Just a little bit, yeah.
And if he goes a little bit further, he's going to lift that last finger, and then he knows he's going way too far.
Yeah, we were definitely wearing personal protective equipment during this entire thing. Lead by example, guys. Come on. But yeah, so you can do sandblasting, you can do heat, or you can do friction, and this exposes the back of the die in order to receive a laser. So these are what's called semi-invasive, because the operational target will still work despite going through hell and back.
It may not always work after the heat, but the first 2 and the last will always work.
And so, we finally get to laser fault injection, the first reason of why you would use a laser against a target. What is laser fault injection? Well, laser fault injection is a technique that you can use light to affect processor functions with nothing more than itself. It typically gets used to cause processors to skip instructions, and the reason why it's so effective is that laser fault injection is normally used in this context to help you bypass security mechanisms on a chip.
It can also be used to modify data on the chip depending on which areas of memory bus you hold. And there's typically 3 ways that you use to actually target the laser. For the methods like Sam was talking, in which you can actually expose the top of the die via sanding or via acid, front side. Back side is typically used when there's no actual shooting on the back of the system, so that you can actually remove the back and then shoot it with a laser, which requires authentication of the circuit so that you can actually hit the back of it. And more commonly now, because of protections, is a lateral side, because the top and the bottom have been started to be shielding, so you're trying to hit the laser beam from the side and just happen to bounce it to where you need it to be inside of the actual RAM chip.
So my next slide is about asking a lot of questions. You guys might know that I really like puns. So this is going to be a theme throughout the entire thing. Right, so hands up, do any of you actually own a laser fault injection rig? Interesting. We have some clever ones in the, yeah, I know, but this doesn't count. This is what the slide's about. Right. So if any of you had actually raised your hands, the next question was going to be, would you be willing to actually tell us how much it costs? Because my next slide was going to say, drinks were on you. The new average cost of a LFI rig on the commercial market at the time that we were doing this research is approximately 150,000 USD. Used or decrepit systems, which don't have a guarantee of functioning, can run anywhere between 5 and 20,000 USD.
And that's a big amount of money to risk for a system that may not work, and it may not even work on the target because the market may be immune to it.
And remember, guys, these prices are pre-tariff. So we don't know if those went up or down. We're going to guess going up. All right, so this causes a little bit of a problem for people who do laser fault injection. For those of you who hate doing expensive reports like I do, the justification for submitting an expensive report for anything between $5,000 and $150,000 to either your own company or the company that you made is pretty high. Especially, and you need to have a receipt for it. And I'm really bad at that. My finance folks will tell you that. So this is a huge problem in the community because whenever you find problems where, let's say, an IC is vulnerable to laser fault injection, or maybe you find something that is vulnerable to fault injection in general, the reasoning we normally get from a client perspective is that, it's too expensive. No one's going to be able to have that anyway.
This is a nation-state level attack. No one's going to be able to do this in the garage. It's going to have advanced hackers, advanced study, 4 or 5 year degree, specialized skill, all that.
And we didn't believe that. Also, I didn't want to submit $150,000 worth of expense report in order to prove it. So that's where Project Lorem started, where it really was an operation to reduce the expense report. So I didn't have to get a lot of receipts, and we could prove that laser fault injection is not a nation-state level attack and something that is very easily done from your own home. In reality, Larry's special focus was to democratize tooling. Too many times, I think this is pretty special to B-sides. Too many times have we been told that we can't do something because it's too expensive. Here we were trying to enable people so that you can do it from your own home, you can learn about it, and you can get better at it.
Yeah, it's like most of the citizen science stuff. If you study enough on how to do it, you can find a cheaper way of doing it with stuff you have at your house if you need to.
Okay, so to start off, we needed to figure out how to build a laser fault injection rig in our own home, which splits it up into the essentials, which are only 3 key items. The first key item is you need an imaging system.
So you can see what you're trying to hit.
You need a positioning system.
So you can aim at what you're trying to hit.
And you need a laser.
Because lasers are cool.
All right, so let's start with the imaging and positioning system, because those are the easiest things to tackle. Traditional imaging systems and laser fault injections are microscopes because they're used for targeting and identification.
So in a number of papers I looked at, they were using this particular trinary microscope as the basis for the system. Reasonably refurb price that you can get on eBay is about $4,000.
Pre-tariff. Let's remember that part. All right, so that's a traditional imaging system used in an LFI. And that's if you were to build it in your own home now. Traditional positioning systems are typically tables or specialized purpose-built motors, and they're used for nano-positioning of the target or the laser, depending on the type of LFI rig you have.
These are also pretty expensive just because of how much it goes to build them and how precise they have to be. So they're about $3,000.
So we're already running up a cost of about $7,000 if you wanted to do this at your own home.
And we haven't even got to the laser parts yet. This
Or
is just hardware.
you could do it our way.
So while searching the internet, we found that this project here, the Open Flexure product, is a microscope that's made for citizen science. And the beauty about this thing is it combines two of the things we need in one package. Notably, the plastic structure allows for it to have a 50 nanometer positioning system that's repeatable and pretty accurate.
So effectively, with a 3D printer and some Amazon parts, total cost running you about $280. You can build an LFI positioning and imaging system in your own house that is missing everything, that is not missing anything aside from the laser. That is a cost reduction of approximately 6,720 USD. That's a lot of money. And we haven't even got to the best part. The last part that we needed to tackle was the laser. So traditionally, laser fault injection rigs work by firing a highly powerful laser in a very short amount of time. So to give you an example, a YAG laser can provide tens of millijoules in less than 10 nanoseconds. And this type of setup can cost about just over 30,000 USD on a good day, and that's just for the laser. That's a bit of a problem. So in order to really tackle this, Larry and I had to ask three major questions. How much energy is actually needed to cause a fault, or also known as a glitch? Did we really need that much energy in that short amount of time? And how much time can we get away with when attempting to cause a glitch? Because at the end of the day, laser fault injection is about inducing faults within an IC. So, do we really need to do these things, or where can we get away with? And that brings us up to the coolest part.
So, traditional research has shown that they need millijoules of power to be able to induce a glitch. But recent research and actual theses have gone and done some more mathematical calculations, and it turns out you only need between 40 and 80 nanojoules, which is an order of magnitude of like power of 6 difference between the two.
And some of you may be wondering, how on earth is that possible? And that is because of the wonderful worlds of physics, or also known as the photoelectric effect.
So the trick is we can use a low power over time and actually build up the charge. As you said earlier, the thing, it's all about how much energy gets to that. Well, they discovered that as long as you put the energy in there before the actual clock pulse happens and it changes state, it holds. So if you put it in there, for example, 25 nanoseconds at 2.5 watts, you get past the threshold of the glitch and can change the state.
So the trick here is to use a low power laser over a longer amount of time instead of instantly with high power. And that is how you can induce a glitch, as long as you do it within the same clock cycle. And a 2.5 watt laser is way easier to source. And when we're in a chicken dinner, we found something on Amazon that hit our criteria.
These were on Amazon for $2 for $9.95.
So
In our price
regarding,
budget.
it's a great budget, guys. My expense report is looking real sexy right now. All right, so before we go on about the lasers, we do want to kind of cover why cheap laser pointers enable us to do this, and why we keep bringing you back to that totally you read OSHA disclaimer that we're definitely going to nod along to here.
So does anyone remember all the stories about green laser pointers in the last 20 years? Does anyone know why those are bad? Well, it turns out that to make a cheap green laser pointer, you basically take a high-power IR laser, the kind that could burn your eyes, and you double the frequency, which goes from IR to green. The problem is these are about 5% efficient. So if you put out 5% of green, let's say a 5 milliwatt green, which is the legal standard in the US, you're actually putting out 95 milliwatt of of IR in the 1064 nanometer range, which would be important for a reason we'll get to later.
So what you're seeing me highlight is when you buy these laser pointers and they're cheaply made, you may be, quote, seeing that frequency, but what is actually outputting in the invisible light spectrum is 10,064 nanometers, which is important because that happens to be the exact IR range and output that we need to induce glitches
because that wavelength is actually, silicon is transparent to, so it can actually, or translucent at least, can go through the actual silicon back of the die and hit the back of the surface.
Yeah. So just to kind of cover, 1064 nanometers is considered one of the most common wavelengths to use when glitching. And it's also considered one of the most effective wavelengths for glitching. But it's not necessary, but we're just kind of highlighting cheaply made products can end up helping us out later on. All right, so we've talked about an imaging position, a positioning system, and a laser pointer from Amazon. If you put that all together, you get the Rave, the first generation affordable laser fault injection rig. Every time I say that line, I feel like a saleswoman, and I hate it.
For absolutely no cost.
For absolutely no cost, you get a laser fault injection rig.
And even better, no expense report.
No expense report? Yes, no expense report. All right.
So we're going to put this all together. So what do we do? So on certain targets where it goes too fast, we use an FPGA to slow the clock down, because that's what actually gives us the time to actually have the charge build up. Then you need an LED to be able to see what you're targeting at. We're using a camera that can see that spectrum, so we're using a 1050 nanometer LED to be able to see through our microscope so we know what we're aiming at. We need a green laser pointer so we can actually cause the glitch. And then we needed the objective from a normal standard microscope to be able to see what we're looking at and target the laser through the actual objective so that the focal length of the objective is that of the laser, give or take the optical resistance of silicon.
So we do have pretty photos to show you what the assembling actually looks like. For those of you who want to stay over, we also have the actual rig right here to show you, give you kind of an idea about what it looks like. But when it's freshly naked out of the 3D printer is on the left. Then when you assemble it with the components, it's on the right. Click.
Yeah.
Click faster. When you load the target, it goes on to the top of the positioning stage. And then this is what the target would look like if you look from the underside with the laser firing up into the silicon. And because Larry actually likes you all and none of you brought laser goggles, he swapped out the laser here for a blue one just to show you that the laser does fire up, and this is what it would look like if it is working today. We did not
make sure it was low enough it would not damage my camera.
Yeah, and we purposely didn't bring the laser. I'm definitely going to say we purposely didn't bring the laser to here, just in case somebody wants to plug this thing in. But you do have a way for us to have a look at it. And the reason and how this is all possible, because we haven't addressed something specific, is the beauty of plastic is that it bends. PLA, when combined with stepper motors, has an
axis flexibility, which allows you to make a lever system that'll give you a nanometer resolution as it goes through the stepper.
Of 50 nanometers. And for context, the size of a human hair is
around 1,000 nanometers.
So this system is accurate enough for us to use for laser fault injection, positioning, and a whole bunch of other things just through 3D print, just through bending PLA. That's it. Actually, normally when I do this talk, I actually bring the naked part without it being attached to the stepper motors, and you can really see it moving. The GIF that you see on the right-hand side, or the left-hand side is the best way that you can see the everything moving when it's not assembled. All right, so we're gonna blast through this part.
Go fast on this one. So basically what you have here is you have the positioning system, which is this system at the top that moves over the axis. You've got the objective, which is the microscope part that has the lens. You've got the stepper motors, which allows it to move back and forth through a controller. You've got the beam splitter, so you can actually shoot the laser and see what you're aiming at. You have the green laser pointer. You have a Raspberry Pi with a daughter board on there to control the stepper motors. We've got a manual trigger if we're trying to test other things so we can actually do glitching manually. We've got the IR that we can actually see the target through, which you can see on this little board here. And we've got the FPGA to slow down the clock and actually do some other analysis while we're doing it.
But does it work? Biozilators.
So this is a GIF video of our setup in the lab. And what you're going to notice here is a green light underneath the thing. There's going to be a LED and a red light over there. When the yellow light blinks twice, we have successfully glitched the chip and gotten to an area of the memory that we're not supposed to be.
So for pre-context, we built a little piece of firmware that was designed to do some mathematics that was associated to different colored LEDs. So if you disrupted the maths on the chip, it would be 1, and if you didn't disrupt it, it would be 0.
If it skipped the instruction or if it changed the addition, it wasn't the right value, the light would come on.
I.e., if LFI was detected, we could actually visually demonstrate it here. So yeah, this is it. And yeah, if you see when it loops over, for those of you not colorblind to the color green, you will see a green flash right underneath the target, and that is the actual laser lasing straight into the target.
Yeah.
There you go. Perfect. Okay, so that was, when we first submitted the talk, our initial idea was to make laser fault injection affordable. We did this under $500. To be more precise, it was $320 at the time that we did this. And we proved that you could do LFI at home with 3D printed materials and everything like that. But why stop there? Much like overachieving people who often get told that we can't do things. We asked ourselves, why should we stop there, and what else can we use the Rave for, if not just for LFI? Because, not everybody does laser fault injection. Could we use a rig like this for something different? So, the first thing we thought about was something completely different, and that's in imaging memory.
Okay, go ahead.
Go for it.
So a few years ago, Bunny Hahn released a paper called IRIS, which is infrared in situ inspection of silicon, and that showed that you can actually see through the back of silicon using a 1050 nanometer LED. So as we talked about a little bit ago, we use that on the bottom of the chip, and so this lets us be able to see the image. Now, we are fortunate in the fact that the camera that we use for the laser was actually rated to be 800 nanometer tolerant, but it actually went all the way to 1200. So we were able to use that to see what we were looking at so we can actually aim through it. And so we owe this part to Bunny Hahn for actually providing us the technique to be able to see what we're trying to shoot.
Because you can do laser fault injection completely blind, but that's kind of useless. The reason why this is kind of interesting is we forgot to mention this is specific about statically imaging chips. So just because you have to see the chip in order to do LFI, you can also statically image the chip using IRIS. So to give you a kind of an example of what this means, using a visible light camera, that is what you would see if you were looking at the silicon. And using IRIS, or our invisible light camera, this is what you could see within the silicon itself. And to kind of further emphasize the fact, using Rave's kind of system of panning and scanning, I do promise you that this GIF was way higher resolution, but turns out you can top out the HD requirements of PowerPoint. So this is a better resolution image. It's very, very sharp, very, very accurate, and it enabled us to really look at the components and exactly what we were looking at, especially if it was a blind analysis. Yeah. All right. So there's more to this. As a result of us combining Rave and Iris during our research, we had to actually check if it worked before we got on stage, right? All part of prototyping is to check it works. And what happened during our research is I happened to, in front of me, have an Arduino Nano that I was decapping. And on the back of it was an FTDI chip. So I was like, okay, cool. I wonder if the Rave plus Iris could image this thing. So we put it on the Rave. We walked away and we came back and it was fully imaged. And what was really interesting is on the left-hand side is the image that we got using Iris and the Rave. Now, hands up, who actually knows what the image on the right is? No? Okay.
It's labeled.
Yes,
Yeah.
yes. All right, so the image on the right is an actual silicon die of what we should have had if we imaged the FTDI chip that we thought we had, the FT232R. What we got was the image on the left, which was a very interesting and undocumented alternative that may or may not have been produced by FTDI themselves. So what we ended up discovering is that I think Larry makes a joke here about hidden object puzzles.
Yeah. So you might see a difference between the two images that you could spot, similar to those little cartoons that we had on the Saturday mornings, like newspaper strips. There's just slight differences between the two.
Slight. And the reason why this was quite very interesting is for us, this was a real life version of us checking our supply chain and finding out that the IC that we had was not the IC that we thought we had. So we ended up being able to use the Rave to start, especially when you start building things at home, and the whole point of this is to make it affordable. How many of you have ordered components online, you've received it, you built firmware for it, and then it doesn't work, and you don't know why? A lot of the times, that's because you received something you didn't think you received something you shouldn't have, and there's no way to tell because you can't see through epoxy unless you have an X-ray. So this thing... Or a belt sander. Yeah, I guess it is semi-invasive. It should still work. So that's why this was pretty happy for us, because we can use the imaging system that we use for the LFI to statically image a chip and be able to verify our own components at home. And that was really cool for us. But why stop there? So what if we've already covered statically imaging chips, right? When the chip is off or it's on your computer and you wanted to check what you got. What if it was possible to dynamically image a chip, i.e. when it's on, can you pull memory?
Off of it with just light beams.
Using just light beams, yes, but really the answer was, can you use affordable tooling to dynamically image chips live and pull memory as they run? And that is where the field of laser logic state imaging, or also known as LLSI, comes into play. So for those of you who don't know what LLSI is, here's a very brief introduction.
So laser logic state imaging is a technique that lets you actually image the chip dynamically over the system. So basically, all the transistors, all the memory in the chip is made up of transistors. And all those transistors are arranged into gates, and each of the gates are arranged into clusters, and some organization of those clusters make up the ones and zeros of your RAM and your memory. Now, each chip is different, so it's not exactly as straightforward as looking at one chip and seeing what the data is. You have to go and pull out a similar chip and then map that chip and see where those regions are and where those bits are. And once you do, you can do side channel analysis and be able to extract the data from your target chip. And this is useful if you're trying to do things like get the key out of something, or if you're trying to figure out what the firmware is and try to reverse that. But you have to map it out, and that's a kind of a lengthy process. That
was a lot of words, so I'm going to use pictures. What does this mean visually? Right. Oh, well, sometimes we go backwards.
It's going to look like a...
all right. So what do we mean by this? Right. So transistors are what hold memory. And transistors being arranged in gates, those clusters represent either a binary 1 or a binary 0. And this is how memory tells you binary. It's literally how the silicon works. So that's, if you use LLSI to image a chip, you get a cluster of images that when abstracted and represented correctly, you can pull out actual memory from the chip as it runs.
And what these images are representing are the interference from the electrical system being turned on those transistors that we're mapping.
You're skipping ahead, sir. We haven't even got there yet.
We'll get there.
So how on earth do you do LLSI, and how is that even possible?
So as I was just saying, when voltage is applied to silicon, it changes the absorption and reflection rate of the silicon. So light passes through it differently. And there's a technique in silicon design called electro-optical frequency mapping, or EEPROM.
EEPROM.
Which can be used to check the fluctuation. So you use it as you're going through a state, and you look at the transistors, see if they're flipping when they're supposed to be flipping as it goes through. Well, someone a few years ago figured out that you don't have to actually change the state if you can modulate the power going into the chip. So rather than actually going from a 1 to a 0, if you take, let's say the voltage of the chip is 1.8 for a high, if you send out 1.85 to 1.95 over a sinusoidal wave around 300K, it modulates, which changes the absorption over that transistor, so that the laser interference can be mapped by a processor or by a receiver.
Because remember, when we're imaging dynamic data, we actually don't want the data to change, because then what the heck are we imaging? We want the thing that we're imaging. So instead we use EEPROM, where we can pause the processor instructions briefly, then fire a voltage ripple through the chip, and then use a laser to measure that voltage ripple to tell us if it is a 1 or a 0 in that specific area, and that is LLSI in a nutshell. Totally hyper simplifying here right now. All right. So again, Operation Overachiever. I just realized this is a 45-minute talk, and we are not on time, so we're gonna have to blast through the slides. But overachieving, because telling us no, it's not possible to use affordable components to do something this crazy, is the fastest way to tell me and Larry to do the thing. So just like we did with LFI, can we use the same principles for the Rave to do it for LSI? So there are 6 major components for LLSI to work for the Rave. First, you need to be able to modulate the target.
Then you need a laser that can actually reflect off the silicon that you can actually read.
You need a sensor to enable to receive the laser you fired back at it.
You need to be able to pan over the system pretty smoothly with very fine precision.
You need signal on noise Jesus.
You need to be able to parse the
Thank
signal
you.
from the noise, because there's going to be very slight variations, around 1 part per million.
And then you need to be able to read the thing, because it doesn't matter if you fire a laser at it. If you can't read it, there's no point of it. So it turns out the Rave does a lot of those things already. So let's start with the laser, because that's got to be different. So the Rave previously used a 1064 nanometer for glitching. This graph represents silicon reflectivity at certain wavelengths. And as you can see, 1064 nanometers is a hot garbage reflectivity rate. So using this graph, we were like, okay, well, we can swap out the laser module. What can we use? And we chose 1300, because it's got a far better reflectivity rate in silicon. And some of you may be wondering, why specifically 1300? And that's because it's cheap as hell.
So it turns out the same wavelength is used for most communication systems and fiber optic cables, and they're very cheap. And what's beautiful about these things is that because they are used for something like communications, they need to have a stable signal, which means they put a diode on there to measure the actual, how much actual light is being emitted. And we can use that, which we'll get to in a second. And the best part is this $6 for all of these.
So why is the diode important? Well, because of the magical world of self-mixing interferometry. I am the only person who can say the slide. So we can actually use the same photodiode that is used to measure the laser output as the receiving sensor to receive the lace that we need in order to read the signal that gets fired from the laser.
Yeah, so as it bounces off a perpendicular surface, it hits all the way back to the diode, and we can actually read the various signals.
So for $6, we just fixed 2 problems. And because the Rave already has everything else from the positioning system and everything else, if we put it all together, all we need to do
is scan over the system with a modulated signal while it's in a pause state, and we can actually extract what the data is. And in fact, if we can't pause the state, but we're using something like a hard-coded key, that hard-coded key is not going to change. So if you scan over the system and you find something that doesn't change, that's probably important.
So does it work? So again, remember, we are trying to prove that you can use affordable components to achieve this level of type of research. And the answer is yes. So in this demonstration, we used a highly reflective surface to prove that you can use these components in order to do the thing. If you want to...
we're using a function generator to actually modify how much reflective is going into that laser assembly right there, and noise signal filtration there with some op amps and some highest speed A to D. But as you can see, the function generator here is sitting at a certain megahertz or certain hertz frequency, and we can also read it here on the oscilloscope that's reading the data coming out of the photodiode on top of the laser from the anemometer.
So in other words, if we send the modulated signal that's meant to represent the change of state of the data that we're trying to read, we are proving that we can actually read the thing. Do not look at me right now, because I'm firing a laser at your head. This is the signal that we're actually receiving. So your battery is running low. Great. I'm gonna slide.
I couldn't plug it in that thing over there. So.
Okay. Let me
Next slide.
I'm trying. It's not working now. We're having some technical difficulties.
Okay.
All right. So that's reflectivity. We proved that we can do it. The last problem that we have to fix is how to make a human readable. All right. So we've achieved signal retrieval. How do we make this readable? And that's through artificial intelligence. Where the irony is that you need to make
You need an AI to be able to make something that's easily read by a human, which is kind of ironic.
We're using a robot to make something human readable. Now, full disclosure, I hate the term AI. I think it's a highly overloaded term, and it's often misused. So let's just call this what it is, and that is machine
Statistical
learning.
Analysis using convolutional neural networks.
Yes.
And don't believe the penguin. ChatGPT did nothing.
All right. So what does this mean? That means that Larry and I had to build a CNN to be able to parse LLSI images in order to read data. Some of you may be asking, why did we use a model instead of something else?
Well, as we pointed out, every memory system is unique, and it can be different between different runs. So we need to be able to map out a chip, and we need to have something that's automatically able to read it so that we don't have to. We can generate a map, but it's much easier if we have something to read the map for us.
So by training a model, we've just made it simpler for our problems in the future, effectively.
And we'd probably jump off a cliff if we had to do this by hand more than once.
Yeah, and a really quick thing here, deadlines are real and we're really bad at them. So this is really important because when we created the model, we used a published data set instead of using images from the rave, and I like to be completely transparent about that. And the reason why is because the process to design a low noise bandpass filter capable of doing this right now is incredibly slow. At the time that we were publishing this research, combining that plus an active LLSI, real systems that do LLSI are also incredibly slow because of the precision that you have to do within the actual scanning across the chip.
Which is slow squared.
Slow squared. So we used training data sets that actually, they represent the same type of data we expect to get at the end of the research that we're doing. Because we were trying to prove that a model can be used to read the LLSI images. All right, so a little bit about the data sets that we used.
So this is a data set here, and this is the chip memory from a processor. It's an S&P 430. And if you look very hard and have very good eyes, you might be able to see a signal here where the lights are slightly more white. But can anyone actually see the pattern? Can you read it very well?
So Larry kind of skipped over a little bit of the part. All right, the training data set is using an MSP 430 SRAM block, and that SRAM block was programmed with 512 bits of no memory. So that's what that was used for the training data set. The training data set of 512 bits, you might be able to see on the actual LLSI image little variations in the image to determine that's where the data actually lives in this specific IC. Hands up, does everybody see what that is?
Okay. Okay.
Here, let me help. Does that help? Here, let me help more. Does that help more? Not really, but you can kind of see the point. We can see the data is there, but we don't actually know what to do with it.
So our first step was to make it a little more readable to all of us. So what we did was we took two images that had different bit patterns, and we subtracted one from the other and took the absolute difference and then put that into a different color channel. For example, blue, because I'm colorblind, but I can see blue a little bit better. So if we do that, can you see them better now?
Now you can see where this SRAM block specifically stored 512 bits of memory.
But you still don't know which ones are ones and which ones are zeros. You just know there's a pattern in each of those locations.
Yeah. So you can see, but you can't understand. So the next thing that we needed to help the model do was identify where the 512 bits were stored, because obviously we're people, so we can see the thing, but we need the model to be able to see the thing. So how do we do that?
So basically we created a search grid. And the reason we created a search grid
is because our laptop is out.
Oh, okay. Well, I guess we're done.
Huh? Yeah, there's no power here.
There's a power over here, but I couldn't plug it into this thing over here.
So I can do this off memory, but it's going to help people to see the thing.
Oh.
Did you not turn it?
I hit the button.
I promise you we're hackers. Yeah, it's charging now. How long does this take to...
Not long. Go ahead and talk, and I'll get it back on.
Oh, now you're going to make me do this based off memory?
Fine, I'll do it off memory. Okay, so
But you need to be able to turn this thing on.
I'll type the password when it comes up. Okay, so if you remember the grid with the blue thing and the red stripes. Well, basically what we're doing is we're trying to isolate where the memory things are, where the bits are. Now, we can't just give it to an AI by itself because there's this thing called bit collisions. And what it basically means is if you have similar patterns inside the data, then it's not going to be able to find it because there's going to be too many false positives. So what we did is we divided it into various quadrants, and each of those quadrants
Keep going.
we go and search the algorithm for. So we do this 512 times for each byte, so we figure out which ones have the most highest correlations. And when there's a high correlation, then that's obviously the area where the system should be. And so we go through that process for all the times, and we're able to isolate which ones actually map to which areas. And once we have that, we can actually go and actually generate an AI with a convolutional network that can actually read the data for us based on the image data system.
Okay, Larry, can you work on that?
Yeah.
I'm gonna have to do this manually. All right, so can everybody hear me still? I'm gonna have to yell. Okay.
The lights on.
Larry kind of covered. Second. Oh. That's one. You covered search grids, right?
Yeah.
Did you do the? Did you do the 512 thing?
Start, yes.
I break things. I don't turn them on. How about now? Does it work now? Did I fail an interview? Is it not working? Can everybody hear me?
Oh.
Oh, perfect. Oh, there you go. Oh. Oh.
Working on it.
Oh. Oh.
Why is it done?
Are you gonna? You're expanding your screen. You want to make it. Yeah.
No.
Well. Extend. This is too funny. This is.
We can hack lasers, but we can't get PowerPoint to work.
That's right.
Okay, screw it. We are gonna do this. All right, we are gonna do this way. Or not. F5. Shift F5. Shift F5. Come on. Shift FN F5.
Okay.
There you go. You didn't see anything. All right. You covered the search grid, right?
Yeah. Sir.
Does everybody want us to kind of go over that again, or are you good? You good?
Okay.
Perfect. All right, so we're dividing by search grid. Now that the model can know how to look, we still need to be able to find the right segment. So each segment has a number of bits. We need to know, or the model needs to figure out which segment has the bits that we actually care about, i.e. part of the 512-bit memory that we're looking for. And this is how we search for it. So I'm going to skip over this slide because we totally didn't just waste 10 minutes trying to work this out. But this slide is kind of covered in the next one, which is if time isn't an issue, a really easy way of training a model is you take one data set and you completely program everything with all ones. And then you take another data set and you completely program everything with all zeros, with the exception of one. And the idea here is that if the model were to find a segment where the exception of one was found, an absolute diff would show an observable change that would represent where that data was stored in that segment. And so if you did that 512 times, you would find the 512 times observable differences amongst the data set. Or if you're really smart with maths and statistics, you can do that way more efficiently, but this is the really slow way that works. So what does this actually mean? This is what I really wanted the slides for. So if you take this LLSI image, and you take this segment, and you take a second LLSI image, and you take the same segment, and you take them apart, and you do an absolute diff between the two. If there is an observable change, i.e. the data between the two is different between 1 or 0, it would show the identified location of where that would show, show up on the LLSI image. And the reason why that's important is the observable change is the representation of the location of where a 1 and 0 is, i.e. training the model of where the 1 and 0 is. Yeah, no, this is actual real data that we do. Like all of these images are real from us working on it.
Like one of those right spots
Is the observable change, yeah.
Yeah, it's an observable change.
So, because remember again, transistors, gates, clusters represent a 1 and a 0. Right now, we're trying to train the model to find where those clusters are, because otherwise it's just random noise. Because the next step is once we have an understanding of where all of the observable changes live, where is this turning off?
I don't.
because you're using more power than
Next time we use my laptop, mate.
I wanted to use your laptop. Okay.
All right. Yeah.
you gotta stick it in, like, you gotta download the laptop.
Yeah, your laptop's off. All right, turn that back on. So the next step is once we figured out where the data is, the next step is to train it on what a 1 and 0 is. And that's through supervised learning. So the slide that we have for supervised learning is literally just saying we use supervised learning to help the model identify what a 1 and 0 is. Barry is completely distracted. And at the end of that, we have a successful model of finding where all the data bits are, and then using supervised learning for the model to know which one of those sectors were a 1 and a 0 in relation to the actual data set. The next slide after this was proving that it works.
This is not going to get any power.
We don't have any power to the laptop.
Yeah, it's not charging it off of the thing.
Yeah. Proving where the data is, where we show you a
Can't sync to it.
fancy green and black terminal of us actually running the model against the data set and it identifying 8 bytes, yeah? Or 1 byte, sorry, of 8 bits, 8 bits of the data that we actually had, and it was accurately by 96%.
96% accurate using a test data set about 1/4 of the actual samples that we had, and was able to actually reproduce the first 8 bits of the entire test sample set.
What I love is this whole thing's recorded right now, so we're getting like extra recording of us debugging poorly on the fly, a laptop not working. But hopefully the laptop does turn back on so we can at least show you the demo. But that was technically the end of the talk in the sense of us proving that you can use affordable materials to do LFI. You can use affordable materials to do LLSI, and it is completely possible to create these systems at home. I am doing this completely off memory. I hope you guys are like appreciating this. Another slide that I'd like to show you is that we do stand on the shoulders of many giants. We mentioned right at the beginning of this talk, we had to combine 9 PhDs to do this. We have 3 special shout outs to specific research topics that made this possible. The first is Bunny Hung's research on iris. That wouldn't, if he had not done that, I definitely fangirled over him a little bit when I met him in person. I was like, dude, that iris research was so cool. But Bunny Hung, thank you again. His iris research was instrumental to our work.
Another one is Martin S. Kelly, who had a couple of different PhD papers on the actual amount of power that was required to actually conduct the glitch. That was very beneficial because we were able to shorten our laser amount.
Oh, yeah. And then the third was a thank you to the Open Flexure project. That is a citizen science project that was designed quickly.
I'm going.
No. We don't have. Show them the demo.
Here's the demo.
Yeah. Yeah, so this is the model actually working against the data set. So we're pulling out that data from the LLSI image, and it's determining what those data sets are.
Yeah. We're showing one read here, but we did a lot of reads, and overall it was 96%.
Yeah, and then if we go back first, we'll go back here. One thing to show you why we use the model. So previously you saw the black and white images. Those are special. I think we got feedback, so we'll walk backwards a little bit. Data set number 1 on the left-hand side, that is a different transistor setup. The one that we created was on the right-hand side, so that is its representation of 0, and that is this SRAM's representation of 1. So that is using the model to tailor it for this specific IC. Okay.
And then it was working.
Okay, I'm clicking through this because we don't have a lot of time.
We have negative time.
Okay, so building an LFI was possible for using less than 500 USD. We can learn chip layouts through imaging, introduce faults in embedded controllers, and because I won an argument, because Larry wanted to make this a bench setup, and I said no, I wanted to throw it into a suitcase, perfect example, so we could do this. We have a portable, movable, and affordable entry-level solution for LFI work, imaging work, and for those of you who want to do LLSI work, you can get started.
And so far, no one has complained about it on TSA.
Yes, so far we haven't been told. So here it is. Here is the references that we use for anybody who wants to look at the slides later. We have the Open Lectures Project, Martin S. Kelly, and Bunny Hung as our special shout-outs, so thank you, Atoli. Some things that surprised us. So I didn't know that LASER was an acronym. You can judge me. I don't care.
I didn't believe that hoarding parts forever would be useful, but it was.
Not all data sheets are real, but the thing that we really wanted to focus on this is how powerful open sourcing and democratizing tooling is. We had a lot of questions of why didn't we sell this? Whilst we were doing this research, we couldn't believe that someone else hadn't done this before. And turns out, exactly 24 hours before we got on stage on Black Hat, my LinkedIn message pops up with a random person that I've never spoken to before, and I'm going to bastardize his name, Jan Tapanen, I think, from Fractal. And turns out Fractal had developed their own under 500 euro version of an LFI rig, and they were using it for their own purposes. They just hadn't open sourced it because it was commercially created by them. So after some discussion right before Black Hat, we agreed and we coordinated the tools to be open source at the same time. So for those of you now giving it a year later, there's not one, not two, but actually 3 different researchers that have come out with an open source version of super ultra affordable tooling. Where a funny thing with ours is another research ended up doing, what did he do?
He did roughly the same thing, but didn't figure out the time variance. So he found an actual person in China to send him a 3-watt laser as an IR, and he actually got it, like 6 of them for $300 and built an entire chip on it. And he used that to do the Raspberry Pi 2030 challenge and was able to actually crack the system.
Yeah, and it was just really cool to see. And he didn't actually know we existed until after he published his research. And then someone reached out to him saying, hey, did you know about these guys? And he's like, why didn't somebody tell me this? This would have saved me like so much time trying to figure this problem out. But things that went horribly wrong. Supply chains and distributors were really difficult for us. Us actually getting something reliably lasing, something reliably modulating. I cannot swear on stage because I'm recorded, but it was a lot.
I would like to mention that I am colorblind, and I feel like that graph over there is just calling me out.
Yeah, so this was a graph we received when we bought a laser module, and that was meant to tell us
something.
If anybody knows what the heck that means, please let us know, because that wasted 2.5 weeks of our time.
Oh, it said follow the red line.
Yeah. Which red line? So graphs that make no sense. And then, costs of R&D. Just because it cost us less than $500 to make the final product does not mean it cost us less than $500 to make during research. So this is a shout out to just kind of explain, it does cost money to do these things, but when you get there, it's worth it. So thank you. Next time you see us Raven, I do love saying that word, we do want to increase the control and precision of the laser, and we also want to lower the noise floor. We want to make this LLSI actually achievable. We want to combine the LFI and LLSI housing, and Chaz, because he's nuts, wants to somehow make this cheaper.
I think he said he wanted to go under 100.
Yeah, so Chaz is currently working on the version 2.0 where he's trying to get it under $100 to do this whole thing. We also want to re-contribute to the OpenFlexure project and improve the 3D print because OpenFlexure was designed for microorganisms and we want to create an LFI specific version for it. But key takeaways.
Lasers are fun, but you need to wear protection. Money is no obstacle because we don't have it.
And open source is king. So thank you for painfully walking through this entire thing with everything breaking.
And helping that debug our laptop.
The QR code is 100% not malware, we promise, but it is the GitHub project where we have published all of this online. If you want to build this yourself, if you want to find all of the components, you want instructions on how to do it, it should be on the GitHub project. Last time
If it's not, yell at Casey Rep. He was the first of the thing.
Yep, Casey Rep is our Android to do that for us. And then thank you. If you want to chat to us, do Hallway Con. We're on Hacker Summer Camp. If any of you are Black Hatters, we also have a booth. Feel free to try and find me. What you may not have seen is there was a Where's Waldo hidden on some of these slides. So extra bonus points for those of you who actually found Waldo. But thank you very much. That's all, folks. Thanks for listening. And remember,
Lasers are cool.
yeah. Jesus. Jesus Christ. Any questions? Oh, the center cry.
Hey, so you're primarily concerned with altering running memory for fault injection, reading SRAM cells to presumably do things like pull encryption keys out of memory. What about flash? Things like that, you know.
Did you take this off? Okay. No, go for it. Just
Sorry, I took this off by reflex. So yes, the laser can still affect flash because it's still memory that's stored. It's not magnetic, so it's still a transistor storing and stuff, I think. So
So for data recovery, this is potentially a...
LSSI should be able to be used for data recovery. I don't think that the ripple in the voltage would cause an issue with it as long as it's in safe levels, but I think it would work, yes.
Okay, thanks.
I've not played around with it, but I do believe it's possible.
Fascinating work.
Thank you.
This is awesome. Yeah, this is amazing work. Just a comment, I guess. There was a paper I saw a while back that was about using, in the subject of like everything being crazy, using liquid nitrogen to remove RAM from a computer while it was running. The liquid nitrogen allowed it to, I guess, remain charged in some way, and then they were able to extract data from it later. That would be a really cool thing to see demoed with this. Like,
this is the nitrogen thing that you were talking about with me, like at 2 o'clock in the morning. It was that PhD paper.
I can't remember.
They use nitrogen to freeze the memory instead.
I mean, that's just cold boot attack. I don't remember something with
Yeah.
lasers on it.
What he's referring to was there was an attempt to use liquid nitrogen to basically reduce the self-discharge rate of
Yeah.
the cells long enough that they could put it into a forensic rate.
Okay.
Oh, here we go. Are you coming up? No? He's like... No. But no, yes, that's another style of attack, definitely.
And it probably would work on the actual extraction.
The only problem with liquid nitrogen in that context is the purpose of this was to prove that you could do stuff at home. And the most dangerous thing about this was lasers.
Well, the other problem is that with the liquid nitrogen, you still got to power up the chip again. And depending on what type of memory it is, like if it's a DIMM memory or something like that, it has to be refreshed. And so while you can pull the clock signal down to 0, which causes it to self-refresh, I'm a little worried what would happen with the voltage of the RAM would happen as you modulate it, because the RAM on a DIMM is set to about at max 1.2 volts, and it doesn't have much of a tolerance over it because of static discharge and kind of stuff. So I'm a little worried what the voltage ripple for LSI would do for a live DRAM of either 3 or 4. It's possible, but I would think that between the voltage going in, it would probably
We're just
policy issue.
answering questions, so we're basically done. Yeah. Sounds good.
Okay, sorry.
Well, thank you very much for attending our talk. Oh, wait, we go. Okay, one more. Okay, go ahead. Quick, fast.
I just wanted to ask you guys if you considered like flight schools for the lasers. A lot of Redbirds have the same setup on their full motion like safety measure. I don't know if it's exact, but I used to build simulators for like Redbird and Cessna and Frasca, and it looked similar. I'm not certain, but a lot of flight schools might have old parts. I got a bunch of that for like $200. It was like,
Hey, that's
so
cool.
just
Yeah.
might want to consider that.
Yeah, definitely. Thank you. Thank you very much. This is why open source is cool, guys. All right. Thank you very much. Let's help B-Sides pack up. Sorry for going over time.